The Education of T.C. Mitz. Preface. This is not intended to be free verse. Writing each phrase on a separate line facilitates rapid reading, and everyone is in a hurry nowadays. Contents. Preface. Introducing the hero, T.C. Mitz. Part 1, The Old. 50 million people can be wrong. Don't hit the ceiling. Tissue paper thinking. Generalization. Our totem pole. The totem pole continued. Abstraction. Define your terms. The wedding. The offspring. A summary of Part 1. Part 2, The New. A new education. Common sense. Freedom and license. Pride and prejudice. Twice two is not four. Abstraction, modern style. The fourth dimension. Preparedness. These moderns. And the last part, the moral. Introducing the hero, T.C. Mitz. This introduces the hero, the celebrated man in the street. T.C. is born and gets an education of some kind, perhaps college, perhaps the school of hard knocks. In any case, he tries to figure out how best to get along. He picks up a lot of contradictory information. The past is antiquated. You must be progressive. The past is wonderful. A new fangled fads are a sign of decadence. Science will save us from superstitious and fraud. Science is the greatest menace yet invented by man. 50 million people can't be wrong. Some races are always wrong. Be practical, learn a vocation. Don't waste your time on mathematics and art. Why be narrow, practical farmer all your life? Get out and learn some theory and find out how to do things in a better way, and so on and so on. He is naturally confused by all this and very much hemmed in. He becomes not only Mitz in name, but has mitts on his fingers and mitts on his toes, and is generally mystified in the brain. This book is an attempt to get a bird's eye view of T.C. Mitz's predicament and to look for a possible egress. To do this vividly, we use pictures whenever possible, and to do it clearly, we use the clearest language man has invented, mathematics. Oh, we know we do not like mathematics, but we promise not to use it as an instrument of torture, but to show what bearing it may have on the contradictory advice mentioned above, as well as on such things as democracy, freedom and license, pride and prejudice, success, isolationism, preparedness, tradition, progress, idealism, common sense, human nature, war, self-reliance, humility, tolerance, anarchy, loyalty, abstract art, and so on. Now and then we shall point a moral, but please do not think we are being didactic and preaching to the reader. The fact is that we are really talking about ourselves, four people along with millions of others, our T.C. himself. Part 1, The Old. Title, 50 million people can be wrong. Let us begin a very simple question. Suppose you had a choice the following two jobs. Job 1. Starting with an annual salary of $1,000 and a $200 increase every year. Job 2. Starting with a semi-annual salary of $500 and increase of $50 every 6 months. In all other aspects, the two jobs are exactly alike. Which is the better offer after the first year? Think carefully and decide on your answer before turning this page. Did you say job 1 is better? And did you reason as follows? Since job 2 has an increase of $50 every 6 months, it must have an annual increase of $100, and therefore it is not as good as job 1, which has an annual increase of $200. Well, you're wrong. For examine carefully the earnings written out below. And it shows a table here. Job 1, first half of the year, $500. Second half of the year, $500. Total for the year, $1,000. Job 2, $500. Second half of the year, $550. Total for the year, $1,050. Job 1, $600. Second half of the year. This is for the second year. Second half of the second year, $600. Total for the year, $1,200. Keeps going on. In the fourth year, job 1, $800, $1,600. Job 2, $800, $850, $1,650. Note that job 1 pays $200 more each year than it did the previous year. Job 2 pays $50 more every half year than it did during the previous year. All this is in accordance with the promises originally made, and yet job 2 brings in $50 more every year than job 1 does. And you can easily see that this will continue to be true no matter what number of years is considered. You are probably surprised, but don't be discouraged, for you are in plenty of good company. Try it on your friends, and you will find out. Unless they have heard it before, they will probably make the same mistake, and you made 50 million people can be wrong. And this is entirely normal. But please do not come to the conclusion that democracy is no good. For 50 million people do not have to be wrong. They may be wrong when they are too hasty and jump to conclusions, as you saw in the problem above. So do not make a similar mistake again by coming to hasty conclusions about democracy. We are coming back to democracy later. In the meanwhile, please remember that you can fool all the people some of the time, but not all the people all the time. And since you are one of the people yourself and don't want to be fooled, if you can help it, you must be prepared to think straight. And incidentally, don't fool yourself either by thinking that this can be done without any effort at all on your part. Perhaps this little book will help to smooth the road for you. The moral: don't be a conclusion jumper. Part 2. Don't hit the ceiling. Let us try another one, and this time give it a little more thought. Suppose you had a paper napkin, say about 3/1000 of an inch thick. That's 0.003. Now lay another similar napkin on top of it. The two will, of course, be twice as thick as one. 0.003 times 2 equals 0.006, or 16/1000 of an inch thick. Now put 2 more napkins on top of that, making 4 in all, which are 0.003 times 4 equals 0.012, or 12 thousandths of an inch thick. Continue this process, each time doubling the number of napkins. Thus, the first time you had 1 napkin, the second time you had 2, the third you had 4, the fourth you have 8, the fifth you have 16, and so on. Doubling the number each time, as we said before. Now continue this 32 times. The question is, how high will the pile of napkins be? Do you think it will be 1 foot high? Or will it be high as a normal room from floor to ceiling? Or as high as the Empire State Building, or what? The correct answer is not necessarily any of these. What do you think? Decide before you turn the page. Shows a table. Let us again make out a table, showing clearly what was done. It shows each row, first time, second time, third time, all the way to the 32nd time, so 32nd rows. And in the first column, it has number of napkins, and the second column has the thickness. The first row for the first time is 1 napkin with 0.003 inches. And second is 2 with 0.006, and so on. And then the 32nd time is a really big number. Looks like 2,147,000. No, wait, more than that. 2,147,483,648 napkins, which equals 6,442,450.9 inches. In other words, the final napkin, what I just read to you, to change this to feet, we must divide it by 12, obtaining 536,871 feet. Or perhaps you'd like the answer in miles. In that case, we could divide it now by 5,280, since you know there are 5,280 feet in 1 mile. Thus, we get nearly 102 miles. Remember, 1 mile is about 20 city blocks. Now imagine a pile of napkins over 100 miles in height. Are you surprised again? Did you get your answer by a hunch? Or did you try to experimentally by actually piling the napkins up? Or did you calculate it as we did? Let's discuss these various methods a bit.
Let us discuss these various methods a bit. As regards a hunch, we wish to make 2 points very clear. 1. Some of our hunches are right and some of them are wrong. The only way to tell which is to follow the hunch and check it up. 2. Scientists and mathematicians also have hunches. Some of their best ideas have been hunches, but these do not become respectable science and mathematics until they are checked and double-checked. This is one very essential difference between the behavior of TC and that of a scientist. TC is apt to think that if he is good at hunches sometimes, he may rely on them always, but the fact is that each individual hunch must be checked and double-checked. Now as regards the experimental method, this is generally known as a very practical method. If you actually do a thing, you cannot fail to get the right answer. Often this is true, but you can easily see that in this particular problem it is scarcely practical to pile up napkins 100 miles high. You would surely hit the ceiling if you tried it. In short, do not be too sure of what is practical until you have examined the problem in question. Finally, we have the method of calculation. This method was, as we saw, by far the best in this case. So let us not say that mathematics is impractical whereas doing things with your hands is practical. This is sometimes true, but not always. If you think the calculations were tedious, LMGISD, we must point out, 1. At least they were not as tedious as piling up the napkins would have been. 2. There is a much shorter way to calculate the answer, but for this you need to know a little more mathematics, namely, a chapter in mathematics known as logarithms. We shall not explain it here, for it is already explained in any book on algebra. You can look it up, and, with a little effort, Thus learn a method which is useful on many occasions. Please remember that it takes a little effort to drive a car, or to swim, or to do almost anything. But, if the result is worthwhile, why growl at the effort? After all, the only way to make no effort at all is to be dead. The moral: wake up and live, and follow your hunches and check them. 3. Tissue paper thinking. Now that you are convinced that we must be careful and think more delicately, you are ready to tackle another question. Suppose there were a steel band fitting tightly around the equator of the Earth. Now suppose that you remove it and cut it at one place, then splice in an additional piece 10 feet long, so that the new band is 10 feet longer than the original one. If you now replace it on the equator, it would fit more loosely, would it not? The question is, how large a space would there now be between the band and the Earth? Would it be large enough for a man, 6 feet tall, to walk through? B. A man to crawl through on hands and knees? C. A piece of tissue paper to just slip through? Answer before turning the page. Did you say C is the right answer? Perhaps this idea flashed into your mind because you felt that 10 feet could not make much difference in a band which was thousands of miles long in the first place. Or perhaps you had learned not to trust a flash too readily, and decided to calculate the answer in the following way. Since the distance around the equator is 25,000 miles, dividing 25,000 miles into 10 feet gives a very small amount, and therefore I still think that C is the right answer. But such a manipulation of numbers can scarcely be called calculating the answer. For what justification is there for dividing these numbers? What is the theory behind this labor? On more careful consideration you must admit that there is really no reason for doing this. In other words, without a theory, a plan, the mere mechanical manipulation of the numbers in a problem does not necessarily make sense just because you are using arithmetic. Now let us really examine this problem sensibly. You probably know that the circumference, C, of any circle, may be found by multiplying its radius, r, by 27, where z is a Greek letter, pronounced pi, and is a symbol whose approximate value is 3 and 1/7. Expressing this fact about a circle more briefly, we may say C equals a, and this is true of any circle, no matter how large or how small. Now if we increase the radius by an amount x, see figure 1, and make a new, larger, circle whose radius is now r plus x SCESSS, the new circumference would now be C equals 27, r plus x, would it not? This may be written C equals 2n r plus 20 times. If we now compare this with the value of C given above, namely, C equals 2n 7r, we see that C is more than 27r by an amount 27 times. In other words, just as 2 plus 7, may be written 5x2 plus 5x7, since in either case the answer is 45. Increasing the radius by x increases the circumference by 27 times or by 6 and 2/7 times x. Now, then, if we increase the circumference by 10 feet, as in our problem, we have 64x equals 10 feet, and consequently x equals 10 plus 67 or x equals about 14 feet. That is to say, an increase in the circumference of 10 feet results in an increase in the radius of about 1 and 1/2 feet, and consequently, B, on page 33 is the correct answer to our problem. So you see, you must not calculate mechanically, like a robot. Now that you have seen a sensible method of solving this type of problem, try this one. Suppose that you went on a long walking tour around the equator. Assume that the Earth is a perfect sphere, and suppose that you are 6 feet tall. How much further would your head go than your feet? Perhaps you are surprised at the very idea that when you go for a walk your head can go further than your feet. Perhaps you think that this is against common sense, but a careful look at the cut below will doubtless convince you that this idea is entirely sensible. For, as your feet travel along the inner circle, your head obviously goes along the outer, dotted, circle. Either the moral, your head can go farther than your feet. IV. Generalization. No doubt you are aware of the fact that the formula about the circle in chapter 3 is algebra, and perhaps you can guess from this that one way in which algebra is different from arithmetic is, whereas in arithmetic we do one specific problem at a time, in algebra we give a general tool for doing many problems of a certain type. Thus when we find the area of a rectangle whose base is 4 inches and altitude 2 in, and get 8 square in, this is arithmetic. But when we write 1a equals ob, which says that to find the area, a, of any rectangle, we must multiply the altitude, a, by the base, b, this is algebra. In other words, Algebra is more general than arithmetic, but perhaps you will say that this is not much of a difference, since in arithmetic we also have general rules, but they are given in words, instead of in letters as in 1. Thus in arithmetic we would say, to find the area of any rectangle multiply its altitude by its base, whereas in algebra we say, EAE but, after AL. You may feel that this is merely a matter of a convenient shorthand rather than anything radically new. Now the fact is that it is not merely a question of a convenient shorthand, but by writing formulas in this very convenient symbolism, especially when a formula is much more complicated than the one given above, we are able to tell at a glance many interesting facts which would be very difficult to dig out from a complicated statement in words. And, furthermore, when we learn to handle the formulas, we find that we are able to solve problems almost automatically which would otherwise require a great deal of hard thinking, just as, when we learn to drive a car we are able to go places easily and pleasantly instead of walking to them with a great deal of effort, and so you will see that the more mathematics we know the easier life becomes. For it is a tool with which we can accomplish things that we could not do at all with our bare hands. Thus mathematics helps our brains and hands and feet, and can make a race of supermen out of us. Perhaps you will say, but I like to walk, I don't want to write all the time, and I like to talk, I don't want to use abstract symbols all the time, to which the answer is, by all means enjoy yourself by walking and talking, but when you have a hard job to do, be sure to avail yourself of all possible tools, for otherwise you may find it impossible to do it at all. And so, if you wish to be an engineer and build bridges and things, you must know mathematics. If you wish to figure out how much money to put away now so you may have a comfortable income in your old age, use a formula. If you want to know how much interest you are really paying when you borrow money or when you buy things on installments, use a formula. And, mind you, these are algebraic formulas. Some of these problems cannot be solved by using arithmetic alone. You would be surprised to know about some of the remarkable and useful formulas that would help you if you would make a little effort to find out about them. In fact, the trouble with the world today is not that we have too much mathematics, but that we do not yet have enough. For there are as yet no powerful mathematical methods in psychology, the social sciences, and other important domains, so that even the best workers in those fields are, figuratively speaking, still using their bare hands, and walking, rather than gliding, and talking in ordinary language. Perhaps, in these domains, we are having fun all right, but we are getting nowhere very fast, for our wars are steadily becoming bigger and better. No doubt someone will say, but the war makers do use modern machinery which is based on mathematics. Science is really to blame for the success of Hitler, and therefore but see the work now being done. Described in 1. Mathematico-deductive theory of rote learning, Yale University Press. 2. L. Thurstone, The Vectors of Mind, University of Chicago Science Series. It cannot possibly guide us to the good life. Now we hope to show here that this is not so, that science and mathematics can not only protect us from floods and lightning and disease and other such physical dangers, but have within them a philosophy which can protect us from the errors of our own loose thinking, and thus they can be a veritable defense against all evil, a totem pole, if we would but examine into them carefully. The moral: streamline your mind with mathematics. Bayar's totem pole. Let us symbolize our totem pole by a column made up of the 5 well-known regular solids, as shown in the drawing on the opposite page, and let us think of the solids as separate rooms, in each of which a certain aspect of science is presented. We shall now take you on a guided tour of these rooms. The first floor, the cube, contains all the scientific gadgets with which we are all so familiar, automobiles and refrigerators and radios and airplanes, and what seems like Googles of others. This is of course also the room in which you will find tanks and bombers and all the paraphernalia of war, and this is why some people say that science is amoral, since it produces, with equal indifference, the peaceful toys we enjoy so much as well as the instruments of destruction. But these people have probably never climbed the magic staircase. A Google is a very large number, namely, 10 degrees, or 1 with 100 zeros after it. The term Google was invented in fun by a nephew of one of our great American mathematicians, Professor Edward Kasner of Columbia University. It is becoming a popular word and will doubtless soon be in the dictionary. If you wish to know more about Google and Googleplex, and many other interesting things, see Mathematics and the Imagination by Kasner and Newman, Simon and Schuster, which leads from the gadget room up into the other rooms of our totem pole. and are entirely unfamiliar with their contents. Let us therefore go up to the second floor, the icosahedron. Here we find a great industrial laboratory. This is where the gadgets are invented, tried out, manufactured. The men working on this level are not advertising and selling. They are inventing. They are told by the people who hire them, we want a brighter light, a cheaper light, a more smoothly running car, an effective defroster for airplanes, and 1,001 other things. These research men do not let their minds roam around looking for interesting problems. Their problems are handed to them, and they must solve them within a very reasonable length of time. Fauisk. Only practical men are wanted here, and not over-sentimental ones, for they may be told at any moment to find effective ways of killing people. They must make the best long-range guns, the best poison gases, the bombs which can destroy the most people. But you thought we promised to get away from all this as we climbed upward, and yet this floor seems to have even more diabolical possibilities than the first one. Perhaps if this second floor were destroyed, the war paraphernalia of the first floor might become obsolete and die out of its own accord. Are not these scientific inventors the real devils after all? But let us climb another flight and see what goes on in the octahedron. These men are doing research in pure science. They are not employed by manufacturers or governments. They are usually professors at universities who select their own problems because they are interested in them. They are not concerned with any practical applications of their ideas. They are the theoretical men. They ask the most useless questions. For instance, what happens when you mix sugar and water and lemon? They call it sugar hydrolysis instead of lemonade. They study it in different solutions, carefully varying the relative amounts of the substances involved, and examine them with a polariscope for days and days, and years, keeping careful records and publishing the results in scientific journals. Will these investigations make them rich, or fat, or benefit them in any practical way? Not at all. Then why do they do it? The answer is that they are just driven by curiosity. Once in a while they are consulted by the men on the second floor, but not so very often. Usually they just write up their results and die without knowing whether these will ever have any practical use. But the fact is that their results are very often, in the long run, used by some second-floor scientist. Indeed, these second-story men find that they must study the work of the pure scientists constantly, but usually it is the work of the pure ones of the past. Work which has already found its way into the textbooks which they have studied at the institutes of technology, rather than the current work, published in the journals of pure science. In fact, the gentlemen working at any given time on the second and third floor seem to have very little in common. The second floor men consider the upper floor men to be wild-eyed, absent-minded college professors. Some of them are perhaps just crackpots. Who knows? It is safer to go to the theory of the established past, which has been duly tried and tested, and, on the other hand, the inhabitants of the third floor look down upon the second-story men, considering them to be mere hirelings and ignoramuses, and prefer to leave their results to the second-story men of the future, who will be in a better position to appreciate them. But, granting even that this will be so, what guarantee have we that the uses that their ideas will find will be decent, moral uses? How do we know that they are not storing up just a lot of additional trouble for the unfortunate future generations? No, let us climb up further, and look at the fourth floor, the dodecahedron. Here we find the mathematicians, not the pure mathematicians, for they live on the fifth floor, in the tetrahedron garret, with the modern artists. The fourth floor mathematicians are the ones who know the classical mathematics of the past and apply it to the scientific findings of the pure scientists of the third floor. They take the scientific data and organize it and study it with all the mathematical machinery at their command. If a second-story man ever happens in on the fourth floor, which is very rare, he can hardly control his laughter. These men seem to him to be even more wild-eyed than those on the floor below. But the guide tells him, "You ain't seen nothing yet. Wait till you see the top floor, the tetrahedron." At least on this fourth floor you hear them mention geometry and algebra and calculus, subjects you have heard about in high school or in college. But on that top floor, they draw geometric figures on donuts and pretzels, no fooling, and on rubber sheets. And they have up their algebras and arithmetics in which 2 × 2 is not 4, in which 3 + 2 does not give the same answer as 2 + 3, nor is 5x6 equal to 6xs. They are indeed fit companions for the modern artists who share the garret with them. They are lucky if they can even get a job. And yet the connoisseurs say that their work is tremendously important for the future. Indeed, If you trace back some of the most practical and useful gadgets, you will find that if it had not been for a series of wild-eyed, impractical men, these gadgets could not exist today, as you will see in the next chapter. 6. The totem pole. Cont. Take the radio for example, with all its variety of concerts and important broadcasts of all kinds. Trace it to the second floor and you will find that many men on that floor have been improving reception by inventing better tubes and aerials, etc. But all this could not have happened had it not been for a man named Marconi, a second-story man, who sent the first crude radio messages, and even his work would have been impossible had it not been for another man, named Hertz, who worked on the third floor, and who proved that the very idea of sending a wireless message was actually possible, since he demonstrated the existence of electromagnetic waves. But where did he get the idea of even looking for these waves? Why, from a fourth-floor man, of course, a man named Clerk Maxwell, who first conceived the idea of waves in an electromagnetic field and applied the calculus to it, obtaining a set of differential equations from which he declared the consequence followed that there must be electromagnetic waves, and, as we have already said, Hertz subsequently proved that he was right, and, obviously, Maxwell could not have done his job had not Newton invented the calculus, and so it goes. Take any gadget you like and trace it back, and you will find that, invariably you will have to go up into all the 5 floors before you can have its complete story. But, you will say, you have not proved your initial point at all, since the same is true of tanks and bombers also, and therefore science is indifferent to good and evil, and is amoral after all. You will soon admit, however, if you read again the story we have told you, more attentively this time, that science is trying to tell you something else, if you will but listen. For instance, go back and you will see that in the little story of the radio, there are Americans, Italians, Germans, Englishmen. If you take the airplane, you will also find Russians, Frenchmen, and others. In short, you will be very much impressed by the fact that science is international, that it is trying to tell us that Hitler's racial theories are utterly false. It is also trying to tell us, if we would only listen, that cooperation is essential for accomplishing things, that it is really absurd for the first and second story men to laugh at those who live upstairs, or for the latter to look down upon the Alice, for they are all needed to do the job. Is not this democracy? Thus we see that science is not amoral, but has a philosophy to offer us, provided that we do not merely identify science with first-floor gadgets, and thus cut off its head. Has a philosophy to offer us, provided that we do not merely identify science with first-floor gadgets, and thus cut off its head, the upper floors, and stop its bloodstream, the interrelationship between all the floors. And as we tell you more about those strange algebras and geometries we mentioned, you will see that mathematics has many important messages for us, that it is trying to tell us that various mathematical systems are possible, that they are all man-made and controllable by man, and that if you apply this idea to the social world, you will realize that it is up to you to build a good world if you want one, that man has a great deal more freedom and creative ability than he is sometimes aware of. The idea of a fixed human nature that has us by the throat, EABS 4 DSSA, J equals, is just a fiction, for the activities on the top floor are trying to tell us that human nature has infinite possibilities. In short, it is not the guns and tanks which are the real evils, for a gun may be a great good under certain circumstances, but rather such false ideas as nationalism, dictatorship, narrow views of human nature 2Bs, are the real devils. Thus false ideas are more dangerous than guns. Guns and tanks are mere tools. They may be used for good or evil, but they are only first-floor gadgets, whereas the philosophy of science, which comes from a contemplation of all the floors, and of their relationship to each other, has for us unmistakable messages. We must rise up above the first and second floors and realize that these alone are not sufficient for the human race, whose nature is so beautifully revealed by a study of science as a whole, which, as we have seen, has internationalism and democracy at its very heart. We therefore advocate 1. A broader view of science which enables us to appreciate the philosophy in it. Science as a whole, as seen in the totem pole, can really protect us from evil. 2. A more appreciative attitude toward the top floor men. By knowing how much we owe to the top floor men of the past, we should stop treating them with the brutality with which, of avosia say ug ttfa. CBSR, PO is so 5 Kajang, Re 3, Keynes copyright or, G2 equals 5 apo psi euros at este. They have been treated just because they do not use their energy to make themselves physically comfortable. And we should stop heckling them by asking them, what is the practical use of what you are doing? Or what does this mean for the average man? Since the truth is that they themselves do not know. Their work is as much a natural phenomenon as a natural oil well or natural gas or mountains or rivers. Let us give them the freedom they need to do what is in them to do. Let us turn their garret into a penthouse, and marvel at their strange products. Perhaps someday we shall find a practical use for them. As has so often happened, and besides, the philosophical implications of their work already make them invaluable to us now, as we shall see. The moral. Oh, listen to the totem pole. You saw in Chapter 4 that generalization is one of the principal advantages that algebra has over arithmetic. In fact, generalization is one of the fundamental methods of obtaining new results in all of mathematics. Perhaps someone will say, but generalization is not the private property of mathematicians. Every man knows that all women are silly. Every woman knows that all men are fools. And everyone knows that all Jews are bankers and communists. We need hardly say that these generalizations are not valid, whereas in mathematics we take pride in making our generalizations with much greater care. Now, in geometry, as you know, we deal with the relationships between points, lines, planes, and so on, and study the properties of various figures, triangles, circles, etc., and various solids, prisms, spheres, etc. And, as you also know, we draw diagrams of plane figures on a blackboard or a piece of paper, and make models of three-dimensional objects, to help us visualize the things we are discussing. But of course you realize that a point drawn on a blackboard with chalk, or on a piece of paper with even the finest pencil or pen, is much too large for a mathematical point, which is supposed to have no dimensions at all, no length, no breadth, no thickness, and, similarly, a circle drawn with even the best instruments is only a crude representation of a mathematical circle. Thus the things with which we deal in geometry are abstractions of HCl things in the physical world, and just because they are abstractions, they are therefore exact instead of approximate. For example, every point on the circumference of a mathematical circle is at exactly the same distance from the center. But you might say, even if they are exact, what good are they when they exist only in the mind? You will soon see what a mathematician can do with abstractions and how they can be applied to the actual world. This power to abstract is one of the outstanding characteristics of human beings as compared with other animals. And this power is used not only by mathematicians, but also by artists, musicians, poets, and all other human beings. Perhaps someday we shall measure a person's humanness by his power to abstract rather than by the IQ for a person who can be loyal to such abstract concepts as truth, justice, freedom, reason, rather than to an individual or a place, has the loyalty of a human being rather than that of a dog. Please do not think that we are using the word dog in a disparaging sense, for they are very dear animals. Remember that you must not be a conclusion jumper, but still they are animals and, not human beings. But what are irate justice, freedom, reason, etc.? Do these words really mean anything? And how can we be loyal to them if their meaning is not clear? Are they not just fakes, invented so that some people can make slaves of others by fooling them with such meaningless abstractions? Now you will see, when you have finished this little book, that these concepts truth, freedom, reason, etc., will become much clearer when we examine into what is meant by mathematical truth, what kind of freedom we have in mathematics, what is considered good reason in mathematics, and so on. You will see that as mathematicians have been gradually forced to consider the fundamentals of mathematics, they have been obliged to consider the very nature of human thinking, both its powers and its limitations. For instance, what is the nature of a proof by human beings for human beings? And, of course, this has a definite bearing on, what are we humans anyway? What is the best that we can expect of ourselves? The moral: be a man, not a mouse. 8. Define your terms. So far then we have said that generalization and abstraction are very fundamental and useful human concepts, and we must emphasize the fact that mathematics is not the only domain in which these concepts are used. For example, a great symphony does not have specific words like a popular song, and thus it abstracts an emotion rather than giving a particular instance of an emotion, and therefore has a wider application. Similarly, a great portrait is more abstract than a photograph, because it does not represent the person as he looks at a particular moment, but abstracts what the artist considers to be the essential character of his subject. Perhaps someone will say, "I agree that this kind of abstraction is good, for I admit that a great portrait has a wider scope than a photograph. But what about these moderns who abstract to a degree where the subject is no longer recognizable at all?" But let us not discuss the moderns here, for remember that this part 1 is called the old, not the new. We shall discuss the moderns in part 2. For the present we merely wish to point out that the concepts of generalization and abstraction, in mathematics, as well as in art, etc., have an old and a new aspect, and the uses of them described above belong to the old in mathematics just as portrait painting is an old form of abstraction in painting, and the new in mathematics, as well as in art, may also sound bizarre to the uninitiated. For example, as we have said before, to a modern mathematician 2x2 does not have to be 4. But do not let this frighten you, for when you have read part 2, you will have become so broad-minded, we hope, that such modern ideas will seem just as reasonable as anything you believe today. But let us not anticipate, and continue with our story. What other fundamental ideas do we find in mathematics? No doubt many of you will say, surely you will discuss the fact that mathematics is a domain in which we prove everything, in which we carefully define all our terms, so that we know what we are talking about, and the moral of this will doubtless be that we should learn to define all our terms in any argument, and thus use the mathematical method as a model. Well, we are sorry to disappoint you, but we must tell you that even Euclid, as far back as 300 BC, already realized that it is impossible to define all of our terms or to prove everything, even in mathematics. For, you see, since in a proof, every claim must be supported by something which has already been previously proved, and every term must be defined by something which has already been previously defined. Obviously then at the very beginning of any system of thought we do not yet have anything to build on, and therefore we must start with undefined terms and unproved propositions. But, you will say, it is not as bad as it sounds, because we can always begin with self-evident truths. This is precisely what Euclid thought he did, and it was quite natural in those days for him to think so. But you will see in part 2 that this is not the modern thing to do at all. However, let us at this moment continue with Euclid. He gathered together the, if ym, ls, geometric knowledge of his time, and arranged it not just in a hodgepodge manner, but, as we said above, he started with what he thought were self-evident truths and then proceeded to prove all the rest by logic. A splendid idea, as you will admit, and his system has served as a model ever since. But, as we promised above, you will see in part 2 the very fundamental changes which mathematicians have been obliged to make in Euclid's system, and, therefore, with all due respect to Euclid, we must not slavishly follow him today, as so many of our geometry texts do. The moral progress is made by respecting tradition without slavishly following it 100%. 9. A wedding. If you look back over the history of the human race, you will find that many useful things from arithmetic and algebra were known as far back as 4000 BC, that geometry reached a high stage of development in the work of Euclid, about 300 BC. Since then many more things have happened in mathematics. 1. Algebra and geometry have both been developed further. 2. They have been combined into a new branch of mathematics known as analytic geometry, by Descartes in the 17th century. 3. Many new algebras, and in this connection read, The Development of Mathematics by E.T. Bell, McGraw-Hill. Many new geometries have been developed. 4. The fundamental ideas of all mathematics have been carefully examined. 5. Logic has been inspected and new logics have arisen. 6. New applications of mathematics to the study of the universe have been made. 7. And, as a result of all this, mathematicians have become much wiser, much more sophisticated, and their common sense has become so enlightened that they cannot help but look upon the more usual common sense of T.C. Mitz as an adult looks upon the common sense of a young child who thinks that every man is his daddy. Of course it takes a great deal of powerful thinking to become a great mathematician, but we believe it is possible to give T.C. a glimpse into the results, without asking him to become a mathematician himself. In this chapter we want to tell him about the wonderful 17th century wedding mentioned in 2. above, and about the offspring. Descartes conceived the idea of associating algebra and geometry in the following manner. If we draw two perpendicular lines, zenithal as shown in the next figure, thus dividing the plane of the paper into 4 quadrants, I, 2, 3, IV, we can associate every point in the plane with a pair of numbers, thus, 3, 2, designates the point which is located 3 spaces to the right of O and 2 spaces up. Similarly, 8, 4, is the point located 8 spaces to the right and 4 up. Note that the first of the two numbers gives the distance along the x-axis, and the second number of the pair gives the distance parallel to the y-axis. And if the first number is negative, like 2, we must go to the left on the x-axis instead of to the right. And, similarly, if the second number is negative we must go down instead of up. Thus, -4, -5, designates a point 4 spaces to the left of O and 5 spaces down. See the diagram on page 96. And of course, -4, 5, means 4 to the left and 5 up. 4, -5, means 4 to the right and 5 down, and so on. By this simple device we can get a picture which gives us the information that is often contained in columns of numbers, and gives us this information much more vividly. For example, if the temperatures at a given place during a certain day are time temperature 2 a.m., 4 degrees 5 a.m. degrees 6 a.m. 3% 9 a.m., 11 a.m. 8 degrees 6 p.m. 9 p.m., 3 degrees. They may be represented graphically thus. Take time 2 a.m. Graphs of this type are doubtless familiar to you, for the practical businessman has seen the tremendous advantage that this pictorial kind of representation has for his business, in advertising, in examining his volume of business, and so on and so on. A physician making his daily visit to a hospital can walk through a ward and see each patient's temperature chart at a glance, and decide quickly where his special attention is required without wasting time to examine many columns of figures. All this is so familiar to TC, that we need not emphasize further this debt that we all owe to the mathematicians for showing us this simple but practical device. But while practical men have merely used this device for these simple purposes, the mathematicians have, by playing with the device itself, put it to infinitely greater use. We shall not give you here the details of how the mathematicians developed this simple device of a graph into a branch of mathematics known as analytic geometry, without which we would not have had Newton's calculus with its tremendously important applications to engineering, physics, chemistry, with the resulting benefits to us in transportation via railroads and ships and planes, in communication via telephone and telegraph and radio, and all the other benefits in diet, health, air conditioning, CLC, for these are all described in other books, and there is no need to repeat these stories here. The moral: why not read some more these stories in your spare time? The offspring. We just want to indicate briefly here one major idea of Newton's calculus. Suppose you are taking a trip in an automobile and traveling at a steady rate of 40 miles an hour. How far can you go in 2 hours? Obviously the simple formula, 2d, distance equals rate x time, will give you a quick answer. But suppose that your rate is not constant. You can easily see that this formula will no longer work, and since we often have need for formulas which will apply to motions in which the rate is not constant. Copyright, XIALOE, degrees QSEN, Vi 9 MCDW equals JF, EE. Let us see how this can be done. To do this easily, let us first plot the graph of equation 2, for the case when r equals 40, namely, 3, d equals 4 odd. We first make a table, by giving t any values we please, and calculating from 3, the corresponding values of d, t Phi, 03, 120, 1, 40, 4, 160, 2, 80, 5 200 and then plot these points. Now since equation 2 may be written r equals t, to find the rate, divide distance by time. We see from the graph that the rate may be found by dividing the value of any dotted line, which represents distance traveled, by the corresponding value of t, and so the graph on page 103 completely shows the motion in question, the time being shown along the horizontal axis, the distance along the vertical axis, and the rate being their ratio, and obviously, a motion having a constant rate will be represented by a straight line. Now, what about a motion in which the rate is not constant? Suppose, for example, that you go at a rate of 20 miles per hour for 1/2 hour, then increase your speed to 40 meters /h, and keep that up for 2 hours, then stop for an hour, and then continue for 3 hours at the rate of 35 meters /h. What would the graph look like? Obviously it would look like this, d, 50 an. Similarly, the following broken line graph tells what story? For each straight portion of the line the rate is uniform, But at each change of slope of the line the rate changes to a new value which remains the same until the next break. Note that at each break the change, as shown in these graphs, is a sudden change. Key 50 no allowance being shown for the process of accelerating or slowing down. To show this process, we must have a curve as shown on page 108, where x is the time and y the distance covered. Here any particular rate is not kept up for an appreciable time but is changing all the time. How can we now catch a thing which is so elusive? That was the problem solved by the calculus. Suppose first that the motion from A to B were a uniform motion instead of an accelerated one. Then it would be represented by the straight line AB instead of the curve AB, and it would show that in time AC the distance BC was covered, at a constant rate equal to BCAC. Now as you take the point B nearer and nearer to A, the straight line AB approaches more and more to the line AD which is tangent to the curve at point A. Thus we may say that the actual rate at A is the limit of BCAC, and whereas this rate lasts only an instant, for as soon as you get away from A the slope of the tangent line is obviously different, still we can catch it and express it mathematically, and thus be able to work with it. Thus, if we represent AC by x, read delta x, which simply means the difference in the x value from A to B, and BC by I, then, as B approaches A, this ratio Ix approaches a limiting value. This limiting value of Ix is represented by di dx, and so we have di dx equals r, the rate at the point A, and r of course changes from point to point. Now, if we know the equation of the original curve, the calculus gives us the necessary machinery, called differentiation, by which we may find di dx at any point, and vice versa, if we know the value of y dx, that is, if we know the differential equation, we can find by means of the calculus by integration the equation of the original curve. Now in most physical problems, in this ever-changing world, the idea is to set up a differential equation which represents what is happening in a small local region, and from this, by integration, to find out for example the entire sweep of the path of a planet. We can hardly expect, from this brief sketch, that anyone can get even a slight idea of the power of the calculus as a tool of science. Suffice it to say, here, that it is a method which enables us to study an ever-changing world, rather than only those things, like the figures in geometry, which very accommodatingly stand still while we are measuring them. It is an instrument for the study of a swift, dynamic world. Why then is it not the last word in mathematics? What more is there to be desired? But wait till you see part IT, the moral. Learn to study on the wing. Xi. A summary of part 1. We have tried in part 1 to give you the following ideas. 1. A man trying to think without mathematics is like a helpless child. See chapters I, 2, and 3. 2. A practical man working with his hands alone, without the aid of theory, may be just a fool. See chapters IT, v. 6. 3. The value of mathematics and science is not limited to the gadgets which they give us, but is also in their philosophy. See chapters V and 6. 4. Generalization and abstraction, two powerful tools of thought, are important in all thinking. You cannot really think without them, but you must learn to use them properly. If used carelessly they are dynamite and may blow you up. See page 75 and page 67. 5. Do not always demand a yes or no answer. For example, shall we cling to the traditions of our great forefathers? Yes or no? The history of mathematics shows just how much of Euclid we must keep and how much we must discard. You will see this in some detail in part 2. But outside of mathematics, in the social studies, you will hear people quoting blindly, quoting the Constitution, quoting Karl Marx, quoting Theodore Roosevelt. By the way, the men who wrote the Constitution, as well as other men so often quoted, would be horrified at some of the applications made by their disciples. Beware of disciples. You must either completely accept or completely reject. In mathematics, however, we do not just quote authority. We say, in the light of our knowledge today, Euclid was right in this and wrong in that, and this is a wholesome way to look at the past. It is partly good and partly bad. We must select, in the best light of our knowledge now. 6. Do not jump at conclusions. See chapters I, 2, and 3. 7. Do not rule out hunches because they are sometimes wrong. Read some of the original writings of Faraday or other great scientists. You will be surprised to find how much of their work started as a hunch. But, 8. Do not think all your hunches are wonderful. Some of them may be terrible. Follow them up cautiously. Encourage them but watch them. 9. Try to judge statements and theories in the light of important long-time activities of the human race, like science or mathematics or art. They reveal human nature better than anything else. In them you will see that internationalism and democracy are very deep in the human spirit. See chapter 6, 10. And so you see that mathematics is not for the engineer only, or only for someone who needs its formulas. It is a way of thinking, a way of life, very important for everyone. 11. Most courses in mathematics do not leave time to consider all these things. They are too full of technique. We must stop now and then, techniques to see what general ideas we can get from them, which will be useful for all of us. Part 2. The new a JF axes, PO equals, PSI equals, O, SER, PTE, 12. A new education. And so you know that algebra is a sort of generalized arithmetic by which more difficult problems may be solved. That geometry is not only the study of various figures in 2 and 3 dimensions, but is also a sample science, the entire structure of which is built up from a few basic postulates, and is therefore a model for any system of thought. That analytic geometry is a combination of algebra and geometry which has proved extremely useful. And that calculus is a powerful instrument for the study of our dynamic world. You know also that mathematics is useful not only as a technique, but also as a sample of a method of thinking. It is clear, precise, brief, many-sided, that a thoughtful study of even a little mathematics can throw much light on many controversies, even with very little use of mathematical technique. See the summary of Part 1. Perhaps you may say, what more can we ask? But the fact is that all the branches of mathematics mentioned in Part 1 had been discovered by the time of Newton, who lived from 1642 to 1727. And it was he who invented the calculus. Analytic geometry dates from Descartes, about 1637. Euclid goes back to about 300 BC, and a good deal of the algebra which is studied in high school and college is spread out from as far back as about 3000 BC, to the time of Newton. Thus, the knowledge of mathematics of the average college graduate stops with what was known about 300 years ago. And yet more mathematics has been invented in the last 100 years than in all the previous centuries taken together. If the same were true about the study of physics, the average college graduate would never even have heard of an airplane or an automobile or a radio. Click. Such a situation in physics would never have been tolerated. Why then is it tolerated in mathematics? Perhaps modern mathematics is so difficult that it can be understood only by a few rare souls? Not at all. Of course it took a few very rare souls indeed, to create it, but these new results are no harder to understand than any of the older mathematics. Perhaps it is just inertia on the part of some educators, and TC, not being aware of what he is missing, does not clamor for it. We feel that he can get even more of an intelligent, general outlook on life from the older ones. Read the next few chapters and see if you agree with us. 13. Common sense. As we have already said, one of the chief values of the study of geometry lies in the fact that it is a model for any science or for any system of thought, since it starts with a few basic ideas from which all the other ideas or propositions are derived by logic. Now Euclid regarded these basic ideas as self-evident truths, and some of them seemed to him so self-evident that he did not think it necessary even to mention them. For example, he thought it was so obvious what is meant by the inside and the outside of a triangle that he did not bother to define them, and no doubt TC is thinking this minute that it is only common sense, and that any fool can see which is which at a glance. But he will soon see the trouble this common sense caused, for we shall now show him that it led to the following absurd proposition: if a triangle is not isosceles, then it must be isosceles. You remember of course that an isosceles triangle is one which has two of its sides equal. In order to follow the proof you may have to recall some of your high school geometry, but that cannot hurt anyone much. Given, then, that AB does not equal AC, we shall now prove that therefore AB does equal AC. First draw AD so that angle 1 equals angle 2, and let FE be the perpendicular bisector of BC. Now, if the triangle were isosceles, AD and EF would be one and the same line. But since the triangle is not isosceles, AD and EF must intersect. Let us call their point of intersection G and now draw BG and CG. Also draw GH perpendicular to AB, and GK perpendicular to AC. Now BG equals CG because any point in the perpendicular bisector of a line is equally distant from the ends of the line. This is a well-known proposition in geometry. Remember, Also GH equals GK because any point in the bisector of an angle is equally distant from the sides of the angle. Another well-known proposition. Perhaps you had better have your geometry book handy. This makes triangle BGH congruent to triangle CGK. Since two right triangles are congruent if the hypotenuse and a leg of one are equal respectively to the hypotenuse and a leg of the other. Another call for that geometry book. Therefore BH equals CK. 1. For corresponding parts of congruent figures are equal. Similarly triangle AG is congruent to triangle AGK, and consequently, A equals AK2. Hence, adding 1 and 2 above, we get AB equals AC, showing that two unequal sides of a triangle must be equal. You probably do not like this result any more than the mathematicians did. Now, if you remember your geometry pretty well, you will immediately say that you know just where the trouble is, namely, that AD and EF intersect all right but not as shown in the diagram, that they really intersect outside the triangle, like this. Here again triangle BGH is congruent to triangle CGK, making BH equals CK, and triangle AG is congruent to triangle AGK so that A equals AK, but now this does not make AB equals AC, since A plus BH now does not equal AB, as it did before, although AK plus KC still equals AC as before. Hence now we do not get the absurd conclusion we got before, but we cannot let you off so easily, because you are using the diagram to prove your point, instead of logic. Perhaps you will demand to know what is the difference. Well, the difference is that diagrams are never used as evidence in geometry. Why? Because geometry is not that kind of subject. It is a subject in which the theorems are derived from the basic postulates by means of logic, and if there is no definition given of outside and inside of a triangle, no argument can be based on such a non-existent definition. Do you think this is just quibbling? But mathematicians have been fooled by this sort of thing before, and are more cautious now, and that is what we recommend to TC also, for how would he like to be accused of a crime which is not even recorded in a law book? Would he not then appreciate a lawyer who would argue that there is no validity in a tacit law? Thus mathematicians too have learned by hard experience not to base an argument on tacit assumptions. Perhaps this brings to your mind cases from modern psychology, in which much damage is done to an individual's nervous system by subconscious ideas, which, if brought up into consciousness, can be treated and eliminated as a source of difficulty. Thus, one modern trend seems to be to turn the light on our subconscious thoughts and rid ourselves of the prejudices and false thinking which may be due to them. The moral: be reasonable by bringing to light your tacit ideas. 14. Freedom and license. As we just saw, one of the tasks of modern mathematical research has been to go back to Euclid, bring to light his tacit assumptions, and make the kind of phony proof shown in the last chapter impossible, at least in Euclidean geometry. And is it not up to us to take a leaf from the mathematician's book, and profit by his experience, by trying to make phony proof impossible also in other domains of argumentation, by not permitting any tacit assumptions? But this is not all. What about self-evident truths which were not tacit, but were expressly stated? Well, one of these even at that time did not seem so self-evident, namely, the one which says that through a given point, which is not on a given line, one and only one line can be drawn, parallel to the given line, known as the famous parallel postulate. Not considering it to be self-evident, Euclid tried to prove it, but without success, and finally listed it as self-evident, although he did not feel so good about it. Then, for several hundred years, outstanding mathematicians again tried to prove it, but again without success. Finally, but not until 1826, a remarkable thing happened. The idea dawned in the minds of several mathematicians at the same time, Lobachevsky, Bolyai, Gauss, that not only is this statement not self-evident, but in what sense is it wine at all? And so they undertook to see what would happen if they assumed that through a given point, not on a given line, two lines could be drawn parallel to the given line, one to the right and a different one to the left. Perhaps TC will immediately object and say, but this is impossible, and will get all excited and draw a diagram like this, and say, can't you see that if you draw two distinct lines through C, as shown, neither one of them can be parallel to AB? For CD will meet AB somewhere to the right, and CE will meet it on the left. A little common sense shows this so clearly, but we must warn TC against that common sense of his. Not that it isn't a good thing, but he must use it with so much more caution than he realizes. Don't forget chapters I, 2, 3 in Part 1, and page 93, and we must also warn him again against this reckless use of diagrams, and compel him to stick to logic as his safest weapon for clear thinking. Now when these three very intelligent men, mentioned above, looked into the matter, quite independently of each other, by the way, they found that no logical fallacy resulted from their strange assumption, but that they got an entirely different geometry, a queer-sounding geometry in which the sum of the three angles of a triangle was no longer 180 degrees, in which the famous Pythagorean theorem was no longer true, and yet the logic was perfect. Well, you may say, so what? A couple of wild-eyed, impractical mathematicians go haywire, lose all common sense, fool around with their silly logic, get ridiculous results. BLECs should get excited about it. Well, TC, what would you say if we should tell you that in 1868 a man named Beltrami found that all this stuff was not just fantastic nonsense but actually applied on a surface called a pseudosphere, and he then understood that whereas good old Euclidean geometry applies on a flat surface, like an ordinary blackboard or a piece of paper, that other geometries are needed for other surfaces, and that it is all very sensible, just as, for example, the geometry on the surface of the Earth is also non-Euclidean, since here too the sum of the angles of a triangle does not equal 180 degrees. Thus consider the triangle formed by an arc of the equator and the parts of two meridians drawn from the North Pole to the ends of this arc. The two base angles here are each equal to go degrees, so that all three angles together do not add up to 180 degrees. What, then, about those self-evident truths? Apparently both Euclid's parallel postulate and the non-Euclidean parallel postulate mentioned above, permitting two parallels through a given point, are equally true. See Non-Euclidean Geometry by Hugh Gray and Lillian R. Lieber, Galois Institute Press. One of them applying on one surface, the other on a different surface, and so gradually the mathematicians have been forced to the position that in mathematics, instead of regarding the fundamental postulates as self-evident truths, as Euclid did, it makes more sense, in the light of the experience described above, to regard them as mere assumptions. In other words, the mathematician now would say if I assume some things and then derive from them other things by the use of logic, without contradicting myself, that is all I ask, for, fundamentally, I am not even concerned with the question of actually finding a surface for which a certain geometry holds, for my job is to find out what straight thinking can do. In a way it is really a psychological problem, and I find that in some ways I have a good deal of freedom, and, in other ways, I am bound tight. Thus, I am free to select any basic assumptions I please, except that they must not contradict each other. In this way, I can develop all kinds of systems of thought. I find that a great many of them, often to my own surprise, actually find applications in the physical world, and, from past history, I feel that many more of them will find applications in the future, but I am really driven by a great curiosity and delight in the truly remarkable worlds I create. They may sound fantastic to the uninitiated, but I find them not only fascinating but they also throw so much light on just what is human thinking anyway. Note that he has a very clear realization of where freedom ends and license begins. He knows full well that he cannot introduce anything into a system which would destroy the system itself by contradiction. Page those pseudo-liberals who try to introduce into a system of democracy ideas which would destroy democracy itself. They ought to be obliged to state explicitly. See that delightful book by C.J. Kaiser called Mathematical Philosophy, A Study of Fate and Freedom. Dutton. Just what they consider to be the fundamental postulates for democracy. They would probably find that a good many things they now advocate contradict some of their fundamental ideas, and they would be obliged to admit that even freedom of speech itself is necessarily limited, since it must not be used to contradict the other postulates for democracy. So that even in a democracy it is not logical to allow an enemy of democracy to use freedom of speech to destroy democracy. Similarly, freedom of enterprise must also necessarily be limited by the other postulates of democracy. And so you see how mathematics can throw light on various subjects which many people discuss glibly and carelessly. Since they have never been trained to examine ideas with that meticulous care with which a mathematician works, there is a model for straight thinking which we all must try to imitate. This is not the noisy argumentation of the pseudo-thinkers. Rather it is quiet, honest, careful, competent. The moral: do not be naive, use the methods of mathematics. Full stop. WHESSYAAI, BHF Street Air CAE. Ae Pelanak SS equals Oper, ABCS. 15. Pride and Prejudice. We hope that by this time you no longer feel that there is only one geometry. Good old Euclid. He may have given me many a headache in high school, but at least he is respectable, and that you will not be inclined to agree with Mrs. Hardy in Andy Hardy Meets Debutante when she says, "Nice people never change," but that you are prepared to agree with the late Supreme Court Justice Benjamin N. Cardozo, who said, "We are to beware of the insularity of mind that perceives in every inroad upon habit a catastrophic revolution." But, if you are still in doubt, we want to give you, in this chapter, a simple but most charming illustration of a geometry which will limber up your mind so beautifully that you will be prepared to glide through this changing world with ease. We must, however, call to your attention the fact that whereas new ideas are many and welcome in mathematics, still they are not just the ravings of any radical child. With this brief reminder, let's go. You know, of course, that in Euclidean geometry, a plane, or even a line, has an infinite number of points. Now, in the geometry which we shall presently describe, this is not so. Here there are only 25 points in the entire geometry, and it is therefore called a finite geometry. Let us designate the 25 points by the 25 letters of the English alphabet, from A to Y inclusive, and let us arrange these letters in 3 blocks as follows. OUUX equals NEON, DOE at Mayolam NI, SSVVAKLM no go RUP or ST, YCFNDVOVOs negative 8Y, MPOXB. Now let us make the following assumptions. 1. A straight line shall mean any row or column in any of the 3 blocks above. Ray Shasi G 253 5 at 75 ers HTO smumdwo moro. 2. A point pair shall be considered congruent to another point pair when both pairs occur in rows, or both in columns, and if the number of steps between the points is the same in both pairs. A base deskan lel te axo el ragas tiny c vet r col s bay klm no gr osk ud, sp a surly pos res, yy, clefenlo vte me dubrvawixs years bpxcroengewpab is congruent to hi, os is congruent to mx, even though os is in a row of the first block, whereas mx is in a row in the second block. AK is congruent to WD, etc., but AB is not congruent to GI, etc. Note also that AB is congruent to TP because we shall consider the number of steps from T to P in the first block to be 1, 4. When we come to the end of a row or column, we continue to count forward by jumping to the beginning of the same row or column. Note also that AB is not congruent to AF since AB is in a row and AF is in a column, whereas in 2. On page 156 it was said that both must be in rows, or both in columns, but not one point pair in a row and the other in a column. Note also that the word congruence here does not mean the same thing as in Euclidean geometry, where congruence involves distance, and 2 line segments are congruent only if they can be made to fit throughout, whereas here, there is no question of distance or fitting, but merely of number of steps also. Straight line here does not have the same significance as in Euclidean geometry. Since here it means only any row or any column, it would be better, in order to emphasize these distinctions, to arrange the blocks as follows. And, surely, now you are not in the least disturbed by having ABCDE called a straight line. Why? Because this is according to the rules of our game. See 1. On page 155, let us now say that 2 straight lines are parallel if they have no point in common. This is a pretty good use of the word parallel, is it not? Hence, KLMNO is parallel to FGHI, since none of the letters in KLMNO occurs also in FGHI, but ABCDE is not parallel to BGLOV, because they both have the point B in common. Here of course there is no question of 2 lines meeting if sufficiently prolonged, because here no prolonging is possible, since there are no points beyond those we have exhibited. The entire set of points is visible at a glance. Note that whereas in Euclidean geometry 2 lines which are parallel not only have no point in common, but also, they are everywhere equally distant. But here, where distance has no significance, this second property disappears, so that 2 such lines as BGLOV and EJOD may be considered parallel without worrying us at all. In other words, one way in which the mathematician is enabled to make up a new system is to take some old familiar word, like parallel, examine into its various properties some of these but discard others, thus obtaining a new freedom without entirely cutting loose from the past. There may be a moral here for TC. a hint of how to proceed when looking for something new. Not to break entirely with the past, but to mold it and modify it to suit new needs. Remember that an entirely new geometry was found by merely changing one postulate. See page 143. Let us now see what a triangle looks like in this new setup. Take for instance the triplet of points, H, L, and R. They form a triangle whose vertices are of course H, L, R, and whose sides are HL, LR, and HR, and since straight line segments are taken only along rows or columns, but not diagonally, we find the side HL in the third block on page 156, LR in the second block, and HR in the first block. Thus the triangle here is completely dismembered, like the lady in Picasso's L'Arlésienne. Incidentally, it so happens that HL, LR and HR are all congruent, since they are all in columns and each is a two-step pair, so that our triangle is equilateral, whereas triangle AB is isosceles but not equilateral, and triangle AST is neither. A circle here is defined, as usual, as a set of points such that any one of them taken with the center gives a point pair which is congruent to every other such pair. Thus, if we take A as center, and AB as radius, then points B, E, I, W, X, and H all lie on the circle, because AB, AE, AI, AW, X, and A are all congruent, so that here a circle has only 6 points on its circumference. eBay AO vat WW. Bixulit section 0 via Eshkakimento. Se OSG re UADPA ogre ses tanta percent cent korun. O on vawar ye MPX berry equals on WNZ. UQAOKEORTEC at SMN do. Now you would be surprised to find that nearly all the Euclidean postulates are meaningful here, in spite of the meagerness of this little geometry, and a great many of the Euclidean theorems hold here also. For example, the three altitudes of a triangle are concurrent, so are the three perpendicular bisectors of the sides, and also the three medians. Furthermore, the point of concurrence of the medians lies on the line joining the other two concurrency points mentioned above, and divides it in the ratio 2:1, just as in Euclidean geometry. Here also, if two sides of a quadrilateral are congruent and parallel, so are the other two sides. The diagonals of a parallelogram bisect each other. The diagonals of a rhombus are perpendicular. At each point of a circle, there is one and only one tangent, that is, only one line which has a single point in common with the circle. In fact, a whole theory of conic sections is possible here, etc. Do we hear some cynics say again, so what if so? Let us point out, 1. This finite geometry actually arises in connection with certain problems in algebra and number theory. You see, Mr. Cynic, do not be in a hurry to call a thing useless. Perhaps you think it is useless only because your knowledge is limited. 2. Note that this entire subject is built up by logic alone, without diagrams. Thus, a triangle, as we said before, see page 162, no longer looks like a triangle. Circles look very strange, completely dismembered, and so on. And all this helps to emphasize relationships without old prejudices, and to realize that geometry is really a matter of logic and not of diagrams. Degrees the moral. Beware of superficial appearances. Get behind them with a clear head, and find out what is back of that good old propaganda. This process may lead you to some strange, dismembered, modernistic things, but do not let the strangeness scare you. Deep-set prejudice may be worse than strangeness. 16. Twice 2 is not 4. Perhaps you have now become so modernistic that you are really no longer disturbed by the funny, dismembered triangles and circles, and that you are even willing to grant that there is some advantage in all this. But twice 2 is not 4. This is really too much. Let us try to make this clear. As we have seen, one way of making progress in geometry is to take some old familiar word, like parallel, and limber up its meaning just enough to make it possible to put it to some new use. See page 161. Now, perhaps you do not realize it, but you have already had similar experiences in algebra. For instance, when you began the study of algebra in your first year in high school, you became acquainted with negative numbers, as distinguished from the ordinary, positive numbers of arithmetic. Thus, if we represent numbers by points on a line, we may place the positive numbers to the right of 0. Thus, TTTTE equals P Gale AOD Ality AE2H0 and the new negative numbers to the left, so that in algebra you were introduced to a whole new set of numbers which do not come into arithmetic at all. And, as you doubtless know, these new numbers are just as practical as the old ones. since, for example, a temperature of 5 degrees below zero, 5 degrees, T.s. just as real as a temperature of 5 degrees above zero, ask Admiral Byrd, and a debt of $50 is just as real, although not as pleasant, as having $50 in your pocket. Ask any man who is being sued for debt, and you remember you then had to find out what is to be meant by adding these new numbers, and multiplying them. Perhaps you remember these new definitions, and perhaps you remember also how strange they seemed to you at the time. Thus the rule for adding a positive number and a negative number is, take the difference of the numbers and then prefix to the result the sign of the larger one, or, in plain English, if you wish to add $5 and $3, the answer is $2, because if you owe $5, and have $3, and wish to balance your account, you pay part of your debt and still owe $2. In other words, addition now means balancing accounts, and you are not in the least disturbed by the fact that when you add, you sometimes subtract, as you may have heard some youngsters say in high school. The fact is that they are using add in the algebraic sense, and subtract in the arithmetic sense, but there is really no confusion if you realize clearly that add in algebra does not have the same meaning as add in arithmetic. Thus, as we said before, you have already had some experience in changing the meaning of a word in mathematics in order to have progress, and those of you who have had some elementary physics are familiar with still another meaning of the word would. For instance, suppose a force of 2 pounds acts on a body, A, in the direction indicated, and suppose another force of 2 pounds acts on A in another direction, as shown. The question is in which direction will A actually move, and how great a force is actually pushing it? You probably remember that this problem is solved by what is known as the parallelogram of forces, as follows. Draw two lines, BD and B, representing the two given forces in magnitude and direction. Thus, EB Fa then complete the parallelogram by drawing DC and DC, then the line BC is the resultant or sum of the two given forces, and from triangle BDC it is quite easy to calculate the length of BC, which in this case is about 2.83 ibs, so that here 2 plus 2 is not 4 but 2.83, and, if the angle at B did not happen to be a right angle, the sum of 2 and 2 would be something else. Thus, in adding forces in physics, we must take this angle into consideration, and for every different angle we get a different answer for 2 plus 2. And yet you will admit that there is no confusion here whatsoever. It makes perfectly good sense, does it not? Now, realizing more than ever that in mathematics we are free to make any assumptions which we find useful, so long as they do not contradict each other, we see that in this way many different algebras, as well as different geometries, can be constructed, and actually have been. Some of these have found marvelous applications, as, for example, Boolean algebra, used in logic, by means of which you can test, for instance, the consistency of a whole set of legal statements by expressing them in algebraic form, in Boolean algebra, and applying to these expressions the rules of manipulation of this algebra. The implications of this tool as an aid to clear thinking for general life situations are not yet fully appreciated, and now to give you an idea of an algebra entirely different from the one to which you are accustomed. Boole first started this idea, 1850. See Papers on Logic by Alonzo Church of Princeton University, Galois Institute Press, 1942. We shall give you here a little finite algebra constructed by Professor Emeritus E.V. Huntington of Harvard University. This little algebra has as its basic postulates nearly all the postulates of ordinary algebra, except one, and yet it has only 9 numbers in it, alias 324, 5 Sorgno, but you must not think of these as being the ordinary numbers which you know. Think of them rather as 9 symbols which you are to manipulate according to certain rules, as if you were learning to play some new parlor game. Thus we shall give you 2 tables in which you may look up the sum or product of any 2 of the numbers. The Fundamental Propositions of Algebra, Galois Institute Press, 1941. Sum table KJURNAOANMSCO. Ako Theokerman MM. Arku.oa no tmnhmmo hi mnno tomaruf amtn yilumo wa ta mela. Lan ayahu ten I no armanloinda mu ahowy plus nme 000 anu a wyo wu inmwoa. Mo on pheno eco oann is omotrmra on nh ala orn 2 krni. On fu krmwnst alan oot plus nmroogrl on mmo puo. OAAMTT MOCU MSECO 710 L00.060 degrees OOSEEE RECO RE OOB REN 2 PU PATATS RTM CO, and an EOSU NESES less, in a 0003 equals a AEY and Y, 20 LL a J2Y. What interests us here is the fundamental idea that various algebras, like various geometries, are possible, that twice 2 may be 4 or not 4, depending upon the algebra in question, that all these algebras and geometries are man-made, that, therefore, there is nothing absolute about any one of them, that none of them represents the truth, and yet all or many of them are extremely useful, that man, even though he has not found, and probably never will find, the truth, yet he can, by his ability to think, do very well for himself, if he would only use it. This does not mean that man can say to God, "See, I am as good as you are. I really do not need you at all. I can get on very well with my own reasoning power." Not at all. We maintain, on the contrary, that man is so far from being as good as God that he will probably never know the truth. This emphasizes man's humility rather than his arrogance. Thus, since man has only his own reason, and not God's, let him use it to the best of his ability, and he will get some very respectable results. But let him never brag that he knows the truth. The moral. At the end of chapter 7 of part 1 we said, be a man, not a mouse, and now we add be a man, but do not try to play God. Inshore. 12. Be yourself. 17. Abstraction. Modern style. You remember that we pointed out on page 82 the importance of abstraction, and we promised there to say more about abstraction as practiced by the moderns. Well, now that you have seen some strange new algebras and geometries, you are prepared to enjoy a more abstract system. Here, instead of having points or numbers as our elements, we shall take the 4 objects: chalk, arity, chair, desk. The sum and product of any 2 of these elements may be obtained from the following 2 tables. Sum table: chalk red, chalk red red chair chair desk desk chalk chair desk chalk red. Multiplication table: chalk red chair desk chalk red chair desk chalk red chair desk desk. Thus chair plus red equals desk and red x chalk equals chalk etc. etc. Of course the words chalk, red, add, multiply, etc. Chalk chair do not have the ordinary meanings, but are manipulated in accordance 184 chalk desk chair red, with whatever rules or postulates we have chosen. In order not to confuse the reader, abstract addition and multiplication are sometimes designated by registered sign and registered sign to distinguish them from ordinary addition and multiplication, for which we use plus and x without any circles around them. Of course copyright and at do not have a specific meaning, and therefore give to the modern mathematician greater freedom to invent and develop all kinds of systems, and some of these systems may turn out to be of great practical value if and when they are applied to definite problems. But the mathematician's job is to have them ready in abstract form so that they may be used in any situation wherever they may be helpful. An important modern trend in mathematics is toward more and more abstraction, and you can see what a source of freedom and power it is. In chapter 20 you will see how this same trend toward abstraction vitalizes and enriches modern art as well. The moral. Go modern, learn to appreciate the abstract. 17. The 4th dimension. Very well, you will say. I am quite willing to grant now that there may be various geometries and various algebras provided we start with various assumptions and give some new meanings to old words, but I still feel that there is such a thing as the truth. I admit that twice 2 is 4 is not such a good sample of it as I once thought, but how about the actual physical world? Surely here we are not so free to make any assumptions we please. Here we must be governed not only by clear mathematical thinking, which forbids only one thing, self-contradiction, but, in the physical world we are also held down by objective facts, which I still regard as the truth. And, since you are quite an educated TC, you may proceed as follows. Suppose, for instance, that someone, let us call him Mr. K, wishes to measure the distance from O to A, and suppose that, for some reason, he cannot measure it directly, but is obliged to do it indirectly, as in so many problems in trigonometry, by measuring OB and AB instead. Using the axes x and y, he can now calculate OA by using the Pythagorean theorem. OA equals V, OB plus AB. Further, suppose another observer, Mr. K, finds it convenient to use instead the axes x and y. He then measures OC and AC, instead of OB and AB as Mr. K did, and calculates OA by means of OA equals V, OC plus ACY. But note well that although K and K have made different measurements, yet they get the same answer. N. Continues TC, who has really been impressed by part 1 and sees the possibilities. N. Mind you, if a still more individualistic gentleman, Mr. K, prefers to use the axes X and Y shown below, MW, he can still calculate OA, although he now measures OD and AD by using a well-known formula from trigonometry. AO equals V, AD plus AD. 2. OD/AD cos 6n, again gets the same answer. Thus I conclude that, in spite of the individualism of K and others, still they can all do business together because they agree on the result, namely, in this case, the length of OA, which I therefore believe to be an objective fact. I believe in the possibility of the good neighbor policy, in which various people can have a certain amount of individualism and yet can agree on certain facts. Well, TC, we agree with nearly everything you said, but we still maintain that the human race does not, and probably cannot, know the facts, and yet your idea of the good neighbor policy is still acceptable. In order to show clearly what our position is, we must make a little detour to discuss what is known as dimensionality. As you know so well, a point in a plane may be designated by a pair of numbers. Thus point A is designated by 4, 3, because it is reached by going 4 units to the right of O and 3 units up. And similarly for any other point in the plane, we therefore say that a plane is a two-dimensional space. Note also that it takes 2 numbers to locate a point on the surface of a globe, namely, its latitude and longitude, and, therefore, the surface of a globe is also two-dimensional, and similarly for any surface, no matter what its shape may be. And now, as you also know, in 3-dimensional space it takes 3 numbers to locate a point. Thus, for example, we must give the latitude, longitude, and altitude. In order to locate a point in the actual world we live in, we must call your attention here to an important idea. In the above discussion we have been talking about locating a point, but suppose we choose some other element, instead of point, say, circle, and imagine any space which we examine as filled with circles of different sizes, with various centers. If we now wish to discuss the dimensionality of the space in question, we should have to proceed as follows. Take first an ordinary Euclidean plane, and imagine it to be covered with circles instead of points, as mentioned above. Now, to locate any particular circle, we should first have to direct you to its center, which would require 2 numbers, and then, to select this particular circle from all the circles of different sizes which have that same center, we should have to give you a 3rd number, namely, the radius. Thus, from this point of view, an ordinary Euclidean plane is 3-dimensional, and, similarly, the ordinary 3-dimensional world we live in is 4-dimensional if we use spheres instead of points as the elements. Thus the dimensionality of a space depends upon the elements chosen, but there is of course, no confusion here, provided we specify the elements. Now it has been found convenient in modern physics to use events instead of points as the elements in describing physical phenomena, and since every event is characterized by 4 numbers, namely, the latitude, longitude, altitude, and time of its occurrence, we may therefore speak of living in a 4-dimensional world without being either confused or mystical. Now let us see what bearing this has on the discussion at the beginning of this chapter. 19. Preparedness. As we have already seen, see page 189, the length of a line CN, a Euclidean plane, using any rectangular axes, is given by the formula D equals Vxt plus y, and, similarly, in 3-dimensional Euclidean space D equals Vx plus yers where xxody equals po, ag. See the diagram on page 201. Note that in this 3-dimensional space, x plus y taken alone, without the z, is no longer the same for different sets of rectangular axes. Thus, if instead of changing the axes, we move OA to a new position, we see that Vx plus y, or Vx plus y, is merely the projection or shadow of OA, or OA, and of course the shadow of an object may change in length as the object is moved around, without changing the length of the object itself. Now similarly it has been found in modern physics that if you take the interval between 2 events, O and A, instead of 2 points, in our 4-dimensional world, the thing that remains constant is Vxt plus 74 plus r, where 7 is related to the 4th number, the time. See page 199, and that what IAE is no longer a constant, just as Vx plus y did not remain constant when going from 2 to 3 dimensions. See page 200. Translated into plain English, this says that two observers, k and k, who are moving relatively to an object with different but uniform velocities, do not both get the same result for that the length of an object is, you might say, just a three-dimensional projection or shadow of a four-dimensional interval. See pages 201 and 202. Well, replies TC, you are beginning to sound a little mystical, and yet when I look at the formulas you gave me, I follow you all right. But, after all, to go back to the question raised on page 192, all you have really done is merely to say that in modern physics you no longer regard the length of an object as an immutable fact, independent of the particular observer, as it was regarded before Einstein. If you want to know more about this interesting point, see the Einstein theory of relativity, the special theory by Hugh Gray and Lillian R. Lieber, Galois Institute Press. Your four-dimensional interval in LKGPAE is the same for k and k, so this is now the objective fact instead of xtit for zz. The principle, however, is still the same. There are physical facts, and we are gradually finding them out. We see, TC, that you are intelligent but 19th century minded. For the modern 20th century physicist realizes now that any facts that he finds are tentative. They represent the best we have in the light of all known observations and experiments at a given time, but he sees clearly that even these observations are man's observations, subject to the limitations of his senses and his mind, and should in no way be regarded as true. As Einstein says, alles was wir machen ist falsch. Everything we make is false. What then is the use of it? The obvious answer is, the proof of the pudding is in the eating. That is, if our science enables us to get around more easily in this complicated world, even if it is no more than a mere system of bookkeeping or a mere mnemonic, it serves to correlate our various observations, so that we can at least remember them and envisage them better. In short, the modern physicist, making his observations in his human way, finds it convenient to take as postulates for physics certain things which he repeatedly observes, and then he develops by means of his human logic certain consequences of these postulates, and, finally, he makes more observations in order to see whether he will observe these consequences which he arrived at by his logic. If he does, he calls his theory good, but he is under no delusion that the theory will remain good in the light of all future observations. Naturally, so long as he does observe what he predicted, he feels good, and we cannot begrudge him this feeling of satisfaction. For it is only fair to admit that, if we compare a scientist's predictions, say Einstein's, with those of other people, we cannot help but be impressed with the much greater success which he has. Thus, when Einstein predicted in 1916 that if on such and such a date, 1919, you should go to such and such a place, Africa, and set up your camera and take a picture of the stars, you would find that their positions on the photographic plate had shifted from their normal positions by a certain tiny amount, about 1.75 seconds of arc. Arid when the scientists followed his directions, they found just what he predicted. If anyone outside of science can match this power of prediction, we shall admit that he has as good an approach as the scientific one, but we need hardly say that this power of prediction has not been matched by the average science heckling, loose-thinking loudspeaker, and that is why we claim that scientific predictions are a triumph of clear thinking even if they are not the absolute truth. And so, a modern scientist no longer sees objective facts, but of invariants under transformations. Thus Vx plus y is an invariant under a rotation of axes in a two-dimensional Euclidean space, but it is not an invariant under such a transformation of axes in three-dimensional Euclidean space. See page 202, and you will no doubt agree that this is a more precise as well as a more modest way of speaking, and, in this way, the scientist also holds himself in readiness for change, for if new observations are made, or if he reconsiders his basic ideas, thus requiring the introduction of new transformations, he will expect to give up his old invariants for new ones, and, being prepared for this possibility, he will not be as startled by changes as were the 19th century physicists when Einstein introduced his new system, so that now, not only has this new system been accepted because it is more adequate than the old one, but the physicists have, as a result of all this, a much more wholesome outlook on their entire activity. The modern viewpoint demands greater flexibility of mind and preparedness for change. Pull your mind out of those muddy old ruts, and adapt yourself to a continually changing world. XX. These moderns let us now return to the top floor of the totem pole, where twice two may or may not be four, where triangles, as well as ladies, are dismembered. In short, where you find the most modern in mathematics, art, music, etc., and let us see what these different domains have in common, that makes them all modern, though they seem so unlike each other on the surface. The modern trends seem to be: 1. Man has begun to realize that he is a very creative animal. He is growing much bolder and venturing out further from his old playgrounds. 2. There is consequently infinitely more variety now than heretofore. 3. In the course of his wanderings, he is finding some very strange things, but he is learning to be less afraid of strangeness. 4. He is becoming more and more interested in abstract things. All this you have been realizing in connection with mathematics throughout this little book. But if you stop to consider modern music or modern aviation or modern art or any other modern domain, you will see that there, too, these characteristics appear, and since you have become somewhat familiar with strange new things, and have grown to like them, we hope you will doubtless look with wonder and admiration at the drawings in this chapter. For a modern education must include at least a little familiarity with the moderns in various domains. You may expect that these drawings will be strange and dismembered, but you now realize that strangeness is a characteristic of modernism, even in mathematics and physics, and you will not be surprised to find that modern art has infinitely more variety than old-fashioned art, just as mathematics today has infinitely more variety than it used to have. And, above all, bear in mind the admonition we gave you on page 71. When we asked you not to inquire of any top-floor man, whether mathematician or artist, what is the practical use of what you are doing? What does this mean for the average man? For, as we told you, nobody knows. The products of the top floor are natural phenomena, the most interesting of all human documents, and if they ever come back as a first-floor gadget, this is not the most interesting thing about them. All. Mi isos hanantivo usaif, zzfha, tn, val ilp, zzziahiihm adlor lnwi, s or, gawy pramis na iini tai, equals tzhl, b, say, as yi vi poa ae31, hafjei, wcg, iwt7, a phi b ran as if inawmlwt1 equals alvacine s equals, li number 3, as oypk, v, the moral: it is possible to have agreement and yet permit different viewpoints. Chapters 18 and 19. Unless we compare the different viewpoints we cannot even speak of invariance. Page 208, which makes isolationism and provincialism ridiculous, and tolerance essential. These invariants may be derived by various observers with equal rights and equal success. Page 190. See Einstein's Theory of Relativity by H.G. and L.R. Lieber, Galois Institute Press 225. But what is it that each observer has the right to do? Obviously only to do his best, judged by strict standards, to measure as accurately as possible, as judged by the best laboratory practice, to think straight, as judged by the best standards of modern mathematicians and logicians, and not merely to heckle. Modesty and humility and self-reliance. Page 181 should characterize man's activity, since his knowledge is only tentative. Page 204. He must be prepared for change. Page 210. But he must progress with a minimum of upheaval. Page 162. Respecting tradition without being a slave to it. Page 117. Clear thinking combined with careful observation are his most practical weapon. Page 206. Common sense can be enlarged and developed and should not remain childish. Page 93. Human nature is not synonymous with money grabbing and throat cutting. Man is a much more complex and interesting creature. Pages 67 and 214. War is not to be blamed on science. Chapters V and 6. We can have freedom without anarchy. Page 174. Democracy is essential to human accomplishment. Page 64 and chapters 18 and 19. But we must be loyal to its basic principles or we cannot have it at all. Page 149. And so on and so on. No doubt you can find many more morals of this kind in mathematics and science and art. For this little book is only a small sample of this point of view from which we consider not so much the techniques, which here are only incidental, as the general methods of man's successful accomplishment. Perhaps we can learn from them how to be equally successful in thinking about the social sciences. For instance, for surely, man, with so much ingenuity and originality, will not let his social problems lick him, but they will not solve themselves. He must allow his imagination greater freedom, as the mathematicians and scientists and artists do, and, at the same time, must bear in mind the limitations of his freedom. And now please turn back to the introduction and read it again, and consider it thoughtfully in the light of what you have read in this little book. Do you agree with us that this material really helps to clarify the meanings of these concepts? Suggested reading: E.T. Bett, The Development of Mathematics, McGraw-Hill, G. Boots, The Laws of Thought, Macmillan, Einstein and Inret, The Evolution of Physics, Simon & Schuster, Mikuel Farape, Experimental Researches in Electricity, Everyman's Library, S.I. Hayaxawa, Language in Action, Harcourt, Brace, L.T. Hodgson, Mathematics for the Million, Norton, E.V., Huntington, The Fundamental Propositions of Algebra, reprinted by the Galois Institute of Mathematics Press from Monographs on Modern Mathematics published by Longmans, Green, Kasner and Newman, Mathematics and the Imagination, Simon & Schuster, C.J. Kaiser, The Human Worth of Rigorous Thinking, Scripta Mathematica Library, Mathematical Philosophy, A Study of Fate and Freedom, Dutton, H.G. and L. R. Leeser, The Einstein Theory of Relativity, Galois and the Theory of Groups, Non-Euclidean Geometry, Galois Institute of Mathematics Press, LLT Hersron, The Vectors of Mind, University of Chicago Science Series, J.W. Young, Fundamental Concepts of Algebra and Geometry, Macmillan, Mathematico-Deductive Theory of Rote Learning, Institute of Human Relations, Yale University Press, Papers on Selected Topics of Modern Mathematics, Galois Institute of Mathematics Press. Date du état UUMTTTTN, G2L 488 4QA39, Lieber. Expert opinion on the education of T.C. Mitz. Albert Einstein. Have studied with pleasure your new book. Beautiful examples. Full stop. Illuminating. Am convinced that your original enterprise will get the recognition it so richly deserves. C.C. A.F. Kaiser, author of The Human Worth of Rigorous Thinking. Before reading The Education of T.C. Mitz had never imagined it possible to do so much to inform, enlarge, emancipate, and honor the human mind. The book is indeed a kind of miracle. It entitles the authors to a high place among public benefactors. E.T. Bell, author of The Development of Mathematics, have been following the education adventures of T.C. Mitz with absorbed interest, and in doing so have, I hope, acquired some education myself. The book should be required reading, especially for non-mathematicians. As for the pictures, they reveal something new and unexpected on each inspection. This book should do more to acquaint Mitz with the spirit of modern mathematics than any other book with which I am acquainted. S's. I. Hayakawa, author of Language in Action. You pick up The Education of T.C. Mitz and the first thing you will say is, what a funny little book. After looking at a few pictures and reading half a page of text, you will not put the book down until you have read it. In the several days since got the book, 4 of my friends have tried to run off with it, and only gave it up after a heated struggle. The Norton Library is published by W.W. Norton and Company Incorporated, 500 Fifth Avenue, New York, New York, 10036.